Hey everyone, welcome to the second part of the lecture for section 2.3 in the book, talking about mathematical modeling. So in this section, what we're going to discuss in sort of a general way is why mathematical modeling is important and why engineers and physicists should care about it and why it's kind of important. Why this class exists is this section, so you should know why it's important and why you should care about it. So let's go ahead and start talking about that. So why should you care about mathematical modeling? And so for this video, I'm going to give you two reasons. This is sort of stuff that's not really in the book. This is sort of just coming out of me thinking about this, why it's an important thing for you to consider, and why I thought it was important since I also have a background in engineering. I've done things from this point of view as well. So the first reason why modeling is important is in system design. What I mean by this is, say you want to design a shock absorbers for a car, shocks for a car, and how do you want them to behave? I mean, do you want them to sit up there and just bounce up and down repeatedly as you're driving down the road? Or do you want it to sort of as quickly as possible come down to a point where it's relatively stable? As we'll see in the end of chapter 3, these are the idea of mechanical vibrations that we'll talk about and how you design the system so it's so-called critically damped, which would mean it gets to a steady state as quickly as possible back to where it was before. Knowing what the mathematical model tells you about your system will allow you to design it so it behaves in a certain way. So mathematical modeling lets you predict how a system is going to react to certain changes, and you can use that to decide how you want to design your system so it reacts in the way you want it to. So if your model can predict what's going to happen when you bump this system, you can decide what sort of things you want to build into it so it reacts in a better way. An example to think about for things like this is shocks and springs for a car, like I talked about earlier. That's really what I think is the main example you can think about for knowing how you want to design your system can help it perform better when you get to actual testing stages. And now the second reason I want to bring up mathematical modeling and why you should think it's important is for doing different types of stuff, it means you have to do fewer experiments. And the big reason you care about this is money. So for if people have done any work in like labs or things like that, doing experiments in a lab is very, very expensive. And if you can do less experiments and still get good results out of it, you're doing a lot better for yourself and for the company you're working for. So if you can use a mathematical model to predict what things are going to work out well in your experience, what things are going to work out poorly, and then only try the ones that are going to work out well, you've saved a lot of money, you saved a lot of time, you saved a lot of energy, and you're going to get your results quicker. And they're going to be better results in the long run because you knew which things to try to give you positive results from the beginning. Right? So if you can just ignore some things that are all that you know are going to be bad, skip them, and just try the ones that are going to be close, are going to be good, you'll save time, you'll save money, and you'll get your experiment done quicker. One of the big examples for this that I like to use because I came from chemical engineering and which people you probably haven't seen yet are chemical interaction models. So there are models that exist for how different molecules will interact with each other based on what kind of groups they have and how the molecules are structured. So you can use those to predict how things will interact and decide if you're doing some sort of distillation experiment what you want to test to see if it works or not. But you'll know from the beginning if stuff really, really isn't going to work, and you can throw that out and not care about it and just focus on stuff that might work or that you think will work. And trying those gives you a decent spread of results, but it's not as much time as it would take if you were to just try everything from the start. All right. I mean, that's really all I want to say for this video. Just a couple little points about why this is important for engineering and physics and science type people when you're going into fields that require it. So when you're going into a field that in engineering you want to design a system to behave a certain way, well, if you use mathematical models, you can at least get a starting point. Maybe this is really, really complicated and you can't model it so well mathematically. But if you can do a simplified version and get a starting point for, I think the resistance should be around here, you can start there and start playing with the numbers a little bit after that to sort of see how it's actually going to behave and what you actually want it to be. But you've started somewhere close. You've narrowed down your search already and you can start there. Along that line, you're going to have less wasted time, less wasted experiments because you know an idea of what you should be looking for in the first place. You know what the model looks like, you know what it should be, and you can just work on certain smaller cases of what you're looking at as opposed to trying to figure it out for everything. All right, so that's it. Um, this is stuff we really won't see in class too much, but this is sort of the big picture of mathematical modeling. Why you should care, why it matters for physics majors and chemists and biologists and engineers, and why everyone should care about mathematical modeling in future careers. Thanks a lot for watching, and with the next videos, we're going to start looking at examples of putting together models. So I will see you looking at those.